Welcome to the Power of ERDC. I'm your host, Tim Reeves. Our nation's inland waterways are a lifeblood of the economy, yet the critical infrastructure that manages them is aging. This presents an immense challenge for innovation. A single component failure could cost millions per day in economic impact, a high-stakes reality that creates a major roadblock and makes it safer to repair with old technology rather than fielding the new risk. However, ERDC is currently designing an innovative model that can test new ideas, reduce risk, and ultimately accelerate the infrastructure advancement our nation needs. The hydraulic structures experiment and validation model will be a one-of-a-kind capability designed to test and validate tomorrow's infrastructure solutions, some nearly to scale, before they go into the field. Joining us today to discuss this effort are Dr. Charlie Birchfield and Bowen Woodson with ERDC's Geotechnical and Structures Laboratory. Gentlemen, good morning and welcome. So let's start off, and Bowen, we'll draft you first here. To start, can you give us a general overview of this model? And I would say hydraulic structures experiment and validation model. I'm going to say it one more time so I don't have to say it the rest of the time. The size, the type of research it supports, and what makes it such, our first of its kind.
Yeah, so what it is really, it's a model. It's a space for us to innovate. It's just at a very large scale. So when we're talking about the scale of this model, it's about a football field long. It's about 30 feet wide and 20 feet tall. So it's going to be embedded into the ground. So it's hard to really get a scale of it, when you just kind of throw numbers out there. But it's really large because it allows us to test really large test specimens. So what we would like to test in here are things like miter gates or Tainer gates, so things that you would find out on the river for our waterways. And then it also allows us to test these with realistic loading conditions. So we can flow water through it, or we can have hydrostatic head where we have, one water level on one side and then another water level on the other side. And we can hook up a whole lot of gauges to it, collect a lot of data, and then we can use that data to inform numerical models. So right now, we have, lots of other things out there in other models, but they're at a smaller scale, and we have numerical capabilities, but we don't really have a way to bridge that gap. So that's what this model does. It allows us to innovate and then to validate these innovations and then transition them out into the field.
So this is kind of a first for us in the podcast series, where usually we talk about things that are already being used, things that are models that are already being used, or capabilities that are already being leveraged. This is the first time we've had something or talked about a topic that is currently being assembled, being designed. And how did that go from a back of the napkin idea to kind of where you are now? And the timeline is, and we'll get to the timeline a little bit later, but kind of going from the back of the napkin idea to where it is now.
Yeah, so this was something that came up, before me, before I came into the fold here. So Dr. Matt Smith, it was one of his ideas, who's our lead technical director of Civil Works. They presented this idea to us, and we took it, and we were using the Other Transactional Authority, OTA, as our route, because this, like I said, this is the first of its kind. So it's a prototype. So it allows us to use that vehicle to work with industry. So Verdantis is our industry partner. We're also working with others across USACE like ERDC. So it's a collaborative effort. It's something that we can work alongside, others in industry and others in government, and then do the design. So right now where we sit, we're about at the 30% design phase. So as we get to the end of this design, if we deem that the design is successful, we'll then transition to another OTA, would be the next route for assembly.
So, and I'm going to jump around, so my apologies for, but Charlie, just real quick, as you think about the scale of this model, what level of excitement do you have as engineers and scientists to say this is going to be something that can have such a role in our infrastructure, and working with folks like the Inland Navigation Design Center and others to bring this to fruition.
So, given the fact that it's like we said, it's a one of its kind. Like there's no other capability, and so what this presents is an opportunity for folks like Inland Navigation Design, as well as practitioners in the field, to be able to get, call it the warm fuzzy, get the confidence that they need that new technologies are going to be functioning and going to be able to be used. Because when you look at inland navigation structures, and we may get to this later, I don't know, but when we look at inland navigation structures, there's $160 billion of the economy that go through inland nav in a year. So when you look at that impact, you have to have the confidence, you have to reduce the level of risk and improve things to the point that when you put something in place that it's going to be there. I mean, the average design life for inland nav structures is somewhere in the 80 to 100 year mark. Most of our inland nav structures at this point are getting close to that or have exceeded that. So we have to, when we look at refreshing or refurbishing these, we've got to make it last.
So going back to you, this model that we mentioned, the size and the complexity of it, how do you currently test? I mean, I know it's first of a kind, but how do we currently test infrastructure components or the numerical models that go into current infrastructure construction and locks and dams and such?
Yeah, so there's several ways. Numerical models is one way. So we just do everything, computationally. So we have researchers across USACE that, have great ideas, and we can model these things numerically. We also have smaller models. Now, smaller models, there's a lot of problems that smaller models can solve, but the scale of those models does not allow us to accurately scale things down to what's representative of real life. So we can't accomplish everything in the scaled models. The other thing that we can do, besides just looking at the whole system, so an entire miter gate system as a whole, so we can take specific components of those at full scale, and we can test them using some of our other capabilities, such as our strong floor that we had in GSL. So, all of these things, what we're doing here is not removing those things and making those things to obsolete, because we're still going to use those for the appropriate problem set. But there's a gap for testing an entire system at a large scale. So this is bridging that gap, and it's going to take us from the innovation and the things that we can do at smaller scales or component level to fielding a system with confidence.
So, Charlie, if you could elaborate on why there is such a risk in fielding new designs. What makes those who have new infrastructure ideas so hesitant to field new technologies on their waterways?
Well, it's a lot like I mentioned. I mean, when you talk 160 billion with a B dollars of commodities and such going through inland nav system over a course of a year, a lot going down could have drastic impact. It's somewhere, and I don't want to misspeak. Mr. Tell, the Assistant Secretary of the Army for Civil Works, quotes the actual numbers quite often, but it's something on the order of 60% of agricultural commodities in the entire United States go through the inland nav waterways. So if you have a lot go down for a day, you can imagine what that impact would be, especially depending on the time of year, things of that nature. So the risk versus reward on potentially incorporating a new technology that may not have the confidence that 100-year-old technology would have, that's where it comes in. So the model will allow us to, in some ways, validate and demonstrate at a large enough scale to accurately depict those load cases and scenarios in a way that helps us validate those and get them to the field quicker. Because once we can validate that, then the practitioners in the field have the confidence that they need to ensure that they're not down for extended periods of time and things of that nature.
On the R&D side, you can imagine, the excitement we have for innovation. You can imagine the hesitancy on those on the other end.
Absolutely.
Yeah.
Just as much as we want the new and great thing to come out and be used, they want their thing to work and work consistently and effectively and efficiently.
They don't live by the whole fail quickly type.
They don't want to fail at all. Any failure is a concern.
Yeah. How will this model and research capability, we talked a little bit, but work to build confidence and de-risk that innovation? I think we mentioned a little bit, but yeah.
Well, they get to see it. It's one of those things of, a computational model is great. And as engineers and scientists, like, we trust those models because we understand the physics and everything that goes into building those computational capabilities. However, it's different when you have a physical specimen that you can physically see, touch, feel, all those things. And having, as Bowen mentioned, like, we can build smaller scale things, but when you look at the scale that this structures model is going to be able to look at, you mitigate the things that the smaller model lacked. And so when you're call it a pitch, when you're pitching this new technology to a practitioner, and you're like, well, we have this model, but it doesn't really represent this, this, and this, but we computationally modeled it and it says this. It's a whole different story when I can go and say, hey, look at here. Here is something you can touch, feel, and see that looks almost identical to what you're going to use. And through the 3-step process, a smaller scale of computational model and the larger scale, we now have the confidence that you can put this in practice and not have any issues.
Yeah. Boone, can you walk us through how a component will like a new lock gate design or would be tested and validated in this model?
Yeah. So, we've mentioned computational models a lot. The computational models are still going to be a huge part of this. So we would build a preliminary computational model based on what we know now. So these computational models are really good. They typically get the physics right. So we would expect to be pretty close with the computational models when we build them. So then we would go out and we would fabricate whatever specimen it is that we're wanting to test. We would take that specimen, put it in our model, and then we would run it against a series of realistic loading conditions. So we wouldn't just build something, run one type of test. We would kind of put it through the gauntlet of whatever we're looking to see with that specific component. So we'd run it, we'd collect a lot of data. Of course, we would have to process, the more data you collect, the more data you have to process, right? So then we process that data, we transition it back to our numerical modelers. They can iterate on the model, improve their model. And then once we know that we have a validated model, then we would transition this to the practitioner for fielding it.
The scale you mentioned earlier, the football size and the 20, so forth and so on. And I think one thing I may not have mentioned is, like, when you put these items in this model, there's water, the forces of the water, and you're like I said, you're running it through the gauntlet. What are some other specs of the model that would help kind of give people the idea of what's actually taking place in it?
So flow rate is one thing, right? So we want it to be, the river moves very quickly, right? So we want our water to move at not at a rate that just represents the Mississippi River or the Ohio River. It's not specific to any type of river, but we want to flow the water and have a fluid structure interaction that is realistic for what that component would see, for what that gate would see. So it's not about saying, okay, the Mississippi River flows at this rate and the Ohio River flows at this rate. We want to excite the structure in a way with flowing water that is realistic, so that we can use that to inform our model. So the metric and what we're trying to hit there isn't necessarily a one-to-one match. It's not necessarily about a one-to-one match. It's about exciting the structure in a realistic way that can inform our models. And it's in a similar way, putting hydrostatic, putting head on it from a water level on the upstream versus the downstream, as much differential as you can get, collecting data there. We could also push on it with hydraulic rams, right? So we can load it with water, and then we can push on it, and we can push these things to failure if we want to, and see how it fails and identify failure modes and limit states. So there's a lot of different ways that we can excite the structure. But in the end, it's just about exciting it in different ways and collecting data that we can transition back to modelers.
So what are some of the first critical components you plan to test? And are there specific recurring failures this model will immediately help address?
Yeah, so ERDC, like we've mentioned many times, is one of our partners on this. So we're working with them to identify a lot of these things. So we have a planned work package that will come online here in starting next year. And in year one of that is one of the big things, is to work with ERDC and others to prioritize a list of things that we would like to test. So we have ideas in mind. Modularity is one of them, like a modular miter gate, right? So having the ability to have a design, no matter what the width is, for example, you can have a modular gate that you can kind of stack together and it's going to work. But there's other, things out there, things that the practitioners have seen that fail consistently. And like Charlie said, we stick to what we know, right? Because there can be risk associated with doing something new. So we can work with those guys, and then we can identify those, and then we'll move forward with actually testing some of those things in the years after.
Charlie, on our previous conversation we had about this, I think you had mentioned that you've already got a list of things. What are some of those? So is that list getting longer?
Oh, absolutely. It gets longer by the day, and the more conversations I have, the more that list grows. We even talked yesterday about new things that are coming online. We have, for instance, one of the big things that's is if you look at our navigation structures across the country, that were built 80 to 100 years ago, fabrication was different, designs were different because everybody was dispersed across the country. We didn't have the connectivity like we have today. And so there's a significant emphasis on standardization. Well, we can explore those options. So as we have to retrofit structures to create more of the standardization, we have the connection of those components and things of that nature. Bowen will be able to investigate in the model. And then also, kind of a buzzword these days is additive manufacturing, and how can we get, additive manufacturing into the navigation space? Well, we have a huge effort on additive manufacturing of critical components, and how can we use new and novel materials and solve, how can we design these components that are lighter weight but stronger and designed differently? Well, as we begin to scale that up from a benchtop, machine up to large scale additive manufacturing, we can actually take those things at scale and bring them over to the model, and then put them in, like Bowen said, realistic loading scenarios to understand how those will really, perform, which again, not only does it validate what we're doing, not only does it give us the data we need to continue those investigations, but it also builds confidence for the practitioners to know that when we do hand it off, that they've got a piece of or part or component that can be leveraged.
Now, the exciting is I'm completely off script now, so forgive me for a second. But as that list grows, right, and as you're like the INDC and others are like, hey, we getting pretty excited for Christmas morning, and you're still in the design phase in a lot of ways. Is that design phase getting impacted by the list of things that has the design changed, or in some ways adding new things or changing things based on the list of things that need to be tested?
No. So the whole goal of this model, and something we've probably failed to mention up to now, is that it's modular. So it's going to have the ability to accept really anything that you can think of from a connection aspect. So we're going to have basically hole patterns right on the walls and on the floor that you can bolt into, and we can get creative with what we do. So if we have a certain specimen that they want to test, the whole intent is that we could accept it. Then on our end, we're going to have to customize a lot of things for the test. It's going to be up to our engineers to take whatever specimen it is and to make it fit within the model. But we're confident that we can do that because we've made the model so modular and adaptable. So that's the intent of the model. So yeah, we have all these other ideas and things that keep coming up, but we haven't seen one to where we're like, well, that's just not going to work. Right. It's not going to fit in our model.
Right.
We know that the things that we want to do are going to work, large scale. Now, not saying that the model can solve all of the world's problems either, right? So, the model is designed to handle certain flow rates and loading conditions and things. But the ones that we think are relevant, and the ones that we've talked to across USACE with others that are relevant and that push the bounds even of what we could look at in the future, we're making sure that we cover those.
All right. So, Charlie, beyond just building confidence, what is the broader impact of this model to the Corps of Engineers? Are we talking about accelerating and fielding new technologies, or is it saving time and money, or is it all three?
It's all of those. If you look at I think it's 80 or 800 to 1 return on investment type thing, 80 to 1, based on just the number of physical models and computational models and time and things like that. We're going to have a huge return on investment on the R&D side. On the technology transition, which is what we're all about, again, it gives us a capability that no one has to demonstrate these technologies and to test and validate these technologies that's never been done before, ever. The only way to do it now would be to convince a lock somewhere to allow us to do this.
Right.
And then,
they're not going to do it. Yeah.
Exactly. Like, hey, we've never put this in a real scenario.
Right.
would you like to, try it? I mean, it's not, it's not an ideal scenario. So this will definitely accelerate fielding because we have the ability to go through these steps.
So a project of this magnitude, this is not this is not something that popped in overnight like we've talked about or will happen tomorrow. The first of its kind in the nation must have a lot of excitement, and I was going to ask you, what's the reaction been across the community of practitioners that in that waterways community?
How quickly can we get it online?
No pressure, right?
Yeah. I mean, that's the biggest thing is, hey, if we're going to do this, how quickly can you get it up and running? And so Bowen is under the gun a little bit. We're doing everything we can to get it online as quickly as we can.
For those, who have not had the opportunity to be, at ERDC here in Vicksburg, driving by, what would they, like I said, the scale of it is pretty big. And what's the level of excitement for you? This is a once in a career type opportunity to have a hand in developing a prototype, a model of this scale, and having a capability like this at your hands. This is not something that everybody in their career has a chance to do. What's the personal, professional excitement you have in this type of project?
Yeah, I mean, it's exciting for sure. So like when you can drive, you drive by, and where it's going to go right now is if you're off of Porter Chapel Road, you can look over and see it. And right now, you'd see a big hole in the ground, but eventually, there we'll see the model. And even from there, you'll see how large it is, but not until you really walk up and look, because it's going to be embedded down into the ground that you can see, and we're not investing this amount of money for this model to be there for a year. We want this model to have a lasting impact and to help really bridge, like we've said, bridge the gap from innovation to fielding solutions. So we want to be able to apply this to a wide set of problems, over many years, to impact use case. So it's something that I think we're all proud of. It's not just a GSL effort either, right? This is a ERDC-wide effort where we're using expertise across, a lot of the labs. So I think there's a lot of people at ERDC, GSL and in other labs that are going to be proud of this, for a long time.
Let's pull on that just for a second. So, I mean, I know this is GSL model and so forth and stuff, but ERDC is very, very good at not being in a silo in a lot of ways. What has been the interest level from some of the other laboratories as far as engineers and scientists that say, I want to get on that list of possible projects?
I mean, we're the Geotechnical and Structures Laboratory. There's a lot of hydraulics that goes into this thing that Bowen and I know nothing about. I mean, and so we have
therapy session for that.
Exactly.
I know nothing about.
Right. And we're very quick to say, like, we understand the structural aspect of it and we understand the loads and all of that, but we don't understand the hydrology. And so leveraging the Coastal and Hydraulics Lab and those experts over there that are world renowned in their field to do that. And then we also have folks from the construction engineering lab that are experts in structural health monitoring. So from a sensor's perspective and understanding they've worked on navigation structures for years. So they have the expertise to know, hey, if we're going to put this in here, this is kind of the things we need to be looking for. These are some critical things. How does that strong wall need to be designed so that we can make sure that we're capturing things and not generating an unrealistic load based off of how the model is going to be designed. So yeah, we're leveraging essentially every lab to some level to get this done.
So looking ahead, the model is slated to come online at FY28. What happens then? I think we kind of talked about, like, have you already told who the first one is as far as, like, does that project know? And what are some of the first ones that are on the list to get the maiden voyage, I guess, per se?
Yeah, so I mentioned earlier, work package, that we're working on that's going to start next year, and we'll identify a lot of those components. So we want to then start fabricating these components in FY28 in parallel to finishing up the model. So, right when we're cutting the ribbon on the model, we have something ready to go. Like, we already will have things ready to put in the model. And the first thing we're going to do is we're going to take what's, really kind of a standard common miter gate, and we're going to run it through the gauntlet, and we're going to make sure, okay, for something that's kind of the current practice and what we see today, we're validating our models with that. So that's a good, first step, right? And then from there, we're going to start pushing the envelope, right? We're going to start taking all these innovative ideas and implementing them in the model and testing those. So we kind of have plans right now from, FY 27, 28, 29, 30, like that thing's going to be running as soon as it comes online.
What is, FY 30, FY 31, we'll look back. What does success look like for either of you? Or for,
Ooh.
I think from my perspective, as a technical director, for me, it's if Bowen has more work than he knows what to do with, I think that's success, because I think getting this model online is going to generate a lot of interest and a lot of work that, we have our ideas, like Bowen said, like we're going to have essentially a control that like we, verify and validate that the model's doing what it's doing. But then we want to hit the ground running, like whatever that crazy idea is, like we're looking forward to it. And I hope to keep him really busy for a long, long time.
What about you, Bowen?
Yeah, I mean, I think that's it. Like right now, we're so focused on getting this thing online, right? And we want to get it up fast, but we can't have our blinders on to, all right, well, then how are we going to use it, right? So that's why we're working, with others right now to go ahead and we're going to be identifying components and fabricating components, on the front end. I think that once we use this thing a couple of times and we get these big returns on investment, that we expect, I think that's the problem that we're going to have. It's not, finding the work. It's finding the time to put everything in the model that everyone's to do. And that's what, success would look like for me. It's just.
And if we're transitioning things out of that on a regular basis, we're addressing the need. I mean, we're keeping the nation's waterways open. We're innovating and driving the Corps' capability forward. If we can do all of those things, that's success.
It's fielding solutions. That's what we want to do here, right? I mean, it's actually putting infrastructure out there and fielding solutions, and then us kind of being that last point to check and to validate everything before we push it out in the field.
Yeah, as we were talking, as we wrap up, I was thinking about the risk and people who are hesitant for risk. I guess this is that seeing is believing component that they always need. So it'll be fun to see. And we'll go ahead and put you down for another podcast. I think, 4 years from now, 3 years from now. And if you have time, he says you're not going to have time, but we'll see if we can get you on another podcast once this is.
Maybe we can take some of these cameras out there and get to down.
Well, that's going to happen. Yeah. So I'll talk to this team and see if we can do it on location. There we go. I think they all just stopped. So, well, gentlemen, thank you for the time. Thank you for the information. And thank you for the enthusiasm. It comes across very obvious in the conversation. So to our audience, thank you for joining us again. For more information on this and other ERDC research, you can email erdicinfo@usace.army.mil. You can also visit poweroferdicpodcast.org for more information on this topic, as well as previous episodes and other topics as well. To that, I say thank you again, and we will see you next time.